American Physics Olympiad, year 2020. F equal MA. First round. Exam A. This year was split by 2 days, and each student can choose any of these days to participate. As usual, it was given 75 minutes for 25 problems. If you want to get more interesting problems, subscribe for this channel. Problem number 1. A ball is launched straight toward the ground from height h. When it bounces off the ground, it loses half of its kinetic energy. It reaches a maximum height of 2h before falling back to the ground again. What was the initial speed of the ball? Solution for problem number 1. Let's write expression for total energy when this ball was just thrown. Total initial energy E0 equal kinetic energy 1/2 mv square plus potential energy mgh. After this ball reached the ground, it bounces off and losing half of this energy. So it means that energy after bounce is equal to 1/2 initial energy E0. After that it reached the height 2h. So it means that this energy equal to 2 mgh. Now we can write total expression for this energy. That will be 4 mgh equal 1/2 mv square plus mgh. From here we can find what was the initial speed. That was square root from 6gh. That's answer E, and that was solution for problem number 1. Problem number 2. A rigid ball of radius big R is rolling without slipping along the rib of a right angle chute, as shown in the figure. Which of the points of the ball have the maximum speed? Solution for problem number 2. Points A and B must be stationary because they are in contact with the rib and the ball is rolling without slipping. Because the velocity at any point is given by v plus cross product of omega and radius vector r, where v is velocity of center point O, omega is angular velocity, and r is radius vector for any point. We have VA equal VB equal 0, VO equal V, VQ equal V plus omega big R, and VP equal V minus omega big R. So we can see that the maximum speed will have a point Q, which is V plus omega R, and that's answer E, and that was solution for problem number 2. Problem number 3. When an axe is swung with the kinetic energy E directly at a piece of wood, the edge of the axe is buried depth big L into the wood. If the axe is swung with kinetic energy 2E, how deep will it be buried into the wood? Assume that the axe is wedge-shaped with a constant angle and that the force per unit contact area between the axe and the wood during the impact is proportional to the depth. Solution for problem number 3. We can write expression for total energy, which is integral from 0 to L by force per unit area multiplied by area dx. And here we know that this force per unit area proportional to depth, and cross-section proportional to depth. So it means that F equal K1x and S equal K2x. So it means that total energy proportional to L cube. It means that L proportional to energy E power 1/3, and it means that if we increase energy twice, we will get length equal cubic root from 2L, and that's answer B, and that was solution for problem number 3. Problem number 4. 4 identical rods, each of mass m and the length 2d, are joined together to form a square. The square is then spun around its center as shown in the figure at an angular frequency of omega. What is the magnitude of the force that the joints between the rods at the corners of the square must bear? Solution for problem number 4. Consider a rightmost rod and consider an arbitrary point dy on this rod, as on a presented diagram. The centripetal acceleration at that point is given by formula radius vector for acceleration equal negative omega square radius vector for this point, which is in other form is negative omega square d on axis x and y on axis y. So it means that the rightward component of centripetal acceleration is omega square d, which is constant along the rod. Thus, the rightward force on the rod is negative m omega square d. In the direction y, due to symmetry, centripetal force is cancelled. Using Newton's third law and the symmetry, we see that the tension in each joint must be in the direction perpendicular to the corresponding diagonal. Thus, we can set up a free body diagram equation for each rod with the two forces at the joints and the centripetal force. Since these forces must cancel, we get 2F cosine 45 degrees equal FCX. And from here we can find that force F equal m omega square d over square root from 2, which is answer B, and that was solution for problem number 4. Problem number 5. A pendulum of length L oscillates inside a box. A person picks up the box and gently shakes it horizontally with a frequency omega and a fixed amplitude for a fixed time. The final amplitude can be maximized if omega satisfied next one. Solution for problem number 5. In the frame of the box, this is equivalent to a horizontal driving force with a frequency omega. To increase the amplitude, the driving should be at a resonance. So, omega equals square root from G over L, which is answer B, and this is the solution for problem number 5. Problem number 6. A planet is orbiting a star in a circular orbit of radius r0. Over a long period of time, much greater than the period of the orbit, the star slowly and steadily loses 1% of its mass. Throughout the process, the planet's orbit remains approximately circular. The final orbit radius is closest to which one? Solution for problem number 6. The angular momentum equal to mvr is conserved. Moreover, since the orbit is always circular, the kinetic energy and potential energy are related by 2k equal negative u. It means that mv square equal gm big M small over r, where big M is the mass of the star. It means that mass of the star proportional to v square multiplied by r, which is proportional to L square over R, where L is conserved. It means that 1% decrease in the star's mass gives a 1% increase in the orbital radius, which is answer B, and that was solution for problem number 6. Problem number 7. An astronaut standing on the exterior of the International Space Station wants to dispose of 3 pieces of trash. They face the station's direction of travel with the Earth to the left. From the astronaut's perspective, the 3 pieces are thrown first left, second right, and third up. To the astronaut's frustration, some of the pieces of trash return to the space station after several hours. They are next one. Solution for problem number 7. By Kepler's third law, we have t squared proportional to a cubed, where t is a period of orbit and a is the semi-major axis. And also we have total energy E equal negative G big M small m divided by 2a. The astronaut's throw has a negligible impact on the total energy of the trash, and hence a negligible impact on A and hence T. In fact, after one full orbit, all 3 pieces of trash simply return to the space station. That's answer E, and that was solution for problem number 7. Problem number 8. The velocity versus position plot of a particle is shown to the left. Which following choices is the correct acceleration versus position plot of the particle? Solution for problem number 8. The equation for this graph, velocity versus position, is v equals cx, where c is constant. Let's take a first derivative for both parts. That will be acceleration a equals cv, but v equals cx. It means that acceleration equals c square x, and this exactly linear dependency, which is graph C. So that was answer for problem number 8, graph C, and that was solution for this problem number 8. Problem number 9. A block of mass m is attached to a massless string. The string is passed over a massless pulley, and the end of the string is fixed in place. The horizontal part of the string has a length L. Now a small mass m is hung from the horizontal part of the string, and the system comes to equilibrium. Diagram not necessarily to scale. Neglecting friction everywhere, the tension at the end of the string is next one. Solution for problem number 9. In equilibrium, the tensions on the both sides of any pulley must be equal for torque balance on the pulley. The same logic applies to the mass. One can think of it as just another pulley. Hence the tension everywhere in the string is mg. That was answer B, and that was solution for problem number 9. Problem number 10. During this process of problem number 9, the block has been raised by approximately a height of which one? Solution for problem number 10. For force balance on the pulley, the strings must attach to it at an angle of 30 degrees to the horizontal. This also implies the mass must be placed at the middle of the horizontal section. Hence, the horizontal section of a string, originally of length L, becomes two tilted sections, each with a length L over square root from 3. The change in length is L multiplied by 2 over square root from 3 minus 1, which is approximately 0.15 L, which is equal to the increase in height of the block. That was answer A, and that was solution for problem number 10. Problem number 11. The maximum tension per area a material can sustain without failure is called its tensile strength. Plain steel has a tensile strength of 415 megapascal. What is the maximum mass one can hang on a vertical steel rod of negligible mass and a diameter of 2 centimeters? Solution for problem number 11. Tensile strength equal force over cross-sectional area, and the force equal mg. So we have tensile strength P equal this expression, and from here we can find what is this critical mass. That will be tensile strength multiplied by P multiplied by R square over G. And after putting numbers, we have approximately 13,000 kilogram, which is answer C, and that was solution for problem number 11. Problem number 12. A point mass M is glued inside a massless hollow rod of length L at an unknown location. When the rod is pivoted at one end, the period of small oscillations is T. When the rod is pivoted at the other end, the period of small oscillations is 2T. How far is the mass from the center? Solution for problem number 12. Suppose that distance from one end is x. So it means that period for this location is 2 pi multiplied by square root from x over g. If we pivot it to the other end, we have 2t equal 2 pi multiplied by square root from L minus x over g. Let's square both equations and divide the second equation by first equation. We have L minus x over x equal 4. It means that x equal L over 5. And the last step is to count what is the distance from the center. That will be L over 2 minus L over 5, which is 3L over 10. And this is the answer D. That was solution for problem number 12. Problem number 13. A ballerina with a moment of inertia I is quickly twirling with angular velocity omega. In her hand she has a pen of mass m at a radius r from her axis of rotation. The ballerina releases the pen. Afterward, what happened to the vertical component of the angular momentum of the system consisting of the ballerina and the pen? You may ignore all friction, but not gravity or normal forces. Solution for problem number 13. There are no external vertical torques in this problem, as both the gravity and normal force are vertical, so the vertical component of angular momentum is conserved. That's answer C. It always stays the same, and that was solution for problem number 13. Problem number 14. Two blocks of mass m are placed on top of each other, and the bottom block is placed on the ground. The ground is frictionless. The static and kinetic coefficients of friction between the two blocks are μs and μk, with μs greater than μk. The blocks are at rest initially. When a constant horizontal force F is then applied to the bottom block, which of the following graphs could show its acceleration as a function of force F? Solution for problem number 14. For small forces, the blocks move together and the acceleration is linear in the force and equal to F over 2m, where slope is 1 over 2m. At a certain threshold, the top block begins to slip, because μk less than μs. The friction force decreases suddenly at this threshold, so the acceleration of the bottom block increases suddenly. For higher forces, the acceleration is again linear in the force, but with a greater slope. The equation for this acceleration is this one, and we can see that slope is twice greater than in the first case. If we check all 5 graphs, we can see that only graph B is a correct answer. That was solution for problem number 14. Problem number 15. As shown in the figure, a vessel contains 2 types of liquid. The liquid with density ρ1 on the top and ρ2 on the bottom. The depth of the top liquid is h1, and the interface area between the top and the bottom liquid is S1. The bottom liquid has a depth of h2. The area of the bottom of the vessel is S2. What is the gauge pressure? Other words, pressure in excess of atmospheric pressure at the bottom of the vessel. Solution for problem number 15. The gauge pressure is 0 by definition at the top, so it is ρ1 h1g at the liquid interface. The pressure then increases by ρ2 h2g from here to the bottom of the vessel, giving the answer this one. So it is answer A, and that was a solution for problem number 15. Problem number 16. Liquid droplets store a given amount of potential energy per unit surface area due to their surface tension. When 2 identical, nearly spherical liquid droplets coalesce on a certain type of surface, part of this energy can be converted into upward kinetic energy, causing the coalesced droplet to jump. Assuming the conversion is 100% efficient, how does the maximum height h depend on the radius r of the initial droplets? Solution for problem number 16. First, let's write equation for initial surface area. That will be for 2 droplets 8 pi r square, and initial volume was 8 over 3 pi r cube, which is 4 over 3 pi big R cube, where big R is the final radius for final droplet. So from here this big R equal cubic root from 2 of small r, and area surface for new droplet equal to 4 to power 2/3 pi r square. Now let's count what is total mass and count what is change of area surface. So total potential energy will be ρ multiplied by volume, which is 8 over 3 pi r cube, multiplied by GH, and that must be equal to surface energy change, which is gamma delta S, which is this expression. And we see that finally we have H proportional to R power negative 1, which is answer D, and that was a solution for problem number 16. Problem number 17. Paul and the giant stands outside on a force meter calibrated in newtons, which reads 5000 newton. Paul is wearing a large cowboy hat, which has horizontal cross-sectional area A equal 1 square meter, and completely covers both him and the scale when seen from directly above. At time t equals 0, rain begins to fall vertically downward on Paul, and any rain that hits his hat is collected in the hat's brim. The raindrops have a constant downward speed of 1 meters per second, and the rain accumulates on the ground at a rate of 1 millimeters per second. What is the reading in newtons on the scale as a function of the time t more than 0 in seconds? The density of water is 1000 kg per cubic meter. Solution for problem number 17. The force on the scale has 3 components. First, Schreck's weight. Second, the weight of the water collected in the hat. And the third, the pressure associated with changing the momentum of the downward falling rain. Component first gives a constant weight of 5000 newtons. Component 2 is equal to the weight of the water collected in the hat. The total volume of water collected is rate R, which is 1 millimeter per second, multiplied by time, multiplied by area of hat, multiplied by water density, and multiplied by G, which is finally 10 multiplied by T. And component 3 can be found by noting that in time T, the total mass is equal to a rate of changing mass over time delta T, which is dm over delta T, multiplied by speed, which is R A rho V, which is 1 Newton. So it means that total reading of this scale equal F1 plus F2 plus F3, which is 5001 plus 10T, which is answer B. And that was solution for problem number 17. Problem number 18. A masslet rigid rod is pivoted at one end and a mass M is at the other end. Originally, the rod rotates frictionlessly about the pivot with a uniform angular velocity such that the mass M has speed v. The rotating rod collides with another mass M at its midpoint, which then sticks to the rod. After the collision, what is the kinetic energy of the system? Solution for problem number 18. Here we have angular momentum conservation. It means that initial angular momentum mvr must be equal to this expression. So from here we can find that v final for first mass equal 4 over 5 v. Now we can count what is the final kinetic energy of this system. That will be kinetic energy for the first mass, which is 1/2 m v final square, plus kinetic energy for another mass, which is 1/2 m v final over 2 square. And finally that's equal to 2 over 5 m v square. which is answer D, and that was solution for problem number 18. Problem number 19. A system of cylinders and plates is set up as shown. The cylinders all have radius small r and roll without slipping to the right with angular velocity omega. What is the speed of the top plate? Solution for problem number 19. Instantaneously, each cylinder can be thought of as rotating about its point of contact with the ground or plate below. The rotating angular velocity is omega. This means that relative to the bottom of the cylinder, the top is moving at speed 2 omega r. So the first plate is moving to the right at this speed 2 omega r. The second plate moves to the right at 2 omega r faster than the first plate. And the top plate moves to the right at speed 6 omega r. That's answer E, and that was solution for problem number 19. Problem number 20. A car is driving against the wind at a constant speed v0 relative to the ground. The wind direction is always opposite to the car's velocity, but its speed fluctuates about an average speed of v relative to the ground. The air drag force is AV relative square, where A is constant and V relative is the relative speed between the car and the wind. What is the average rate P of energy dissipation due to the air resistance? Solution for problem number 20. Let's define U as V0 plus V. Here V0 is constant and V fluctuates. Then a relative speed of the car and wind is U plus delta U, where delta U average to 0. The instantaneous energy dissipation rate is force F multiplied by V0, and when we put expression for force, we finally have this expression. Here U square is constant, average for second member is 0, and the third member is always positive. It means that P greater than A V0 U square. And this is answer B, and that was solution for problem number 20. Problem number 21. A circular table has radius r and n greater than 2 equally spaced legs of length h attached to its perimeter. Suppose the table has a uniform mass density with a total mass m, and neglect the mass of the legs. Assuming the table does not slip, the minimum horizontal force needed to tip over the table is next one. Solution for problem number 21. Let's label the tops of two adjacent legs by B and C. The best way to push is to push directly opposite the table from the midpoint of BC directly towards this midpoint. When the table is about to tip over, these two legs will bear all of the weight of the table, and hence provide all of the frictional force. Balancing torques on the table about the axis BC, we have Fh equal mgl, where L equal r cosine theta over 2 or r cosine pi over n is the distance from the center of the table to the midpoint of AB. Solving for F gives the answer. F equal mgr over h cosine pi over n. Note that the credit was given for both choices B and C, since they are equivalent. That was a solution for problem number 21. Problem number 22. A collision occurs between two masses. In each internal reference frame, one can compute the change in total momentum, delta P, and the change in total kinetic energy, delta K, due to the collision. Which of the following is true? Solution for problem number 22. In a collision, momentum is conserved whether the collision is elastic or inelastic. This means that delta P equals 0 regardless of a reference frame, so delta P does not depend on frame. In an elastic collision, delta K equals 0, which is again independent of frame. In an inelastic collision, whatever kinetic energy is dissipated will go to heat up the masses, assuming they are isolated, and energy can only go into thermal energy. The heat capacity and the temperature change of the masses are both frame invariant, so the kinetic energy dissipated is again independent of a reference frame. This can also be shown more straightforwardly by direct calculation. That's answer A. Delta P and delta K do not depend on the frame, and that was solution for problem number 22. Problem number 23. Steve determines the spring constant K of a spring by applying a force F to it and measuring the change in the length dx. The tools he uses to measure F and dx both have a constant absolute uncertainty, leading to an uncertainty in K of delta Ks. If Tiffany measures the same spring constant with the same tools, but by using a force that is 5 times larger, what will her uncertainty in K be in terms of delta Ks? Solution for problem number 23. First, let's write hook law for this spring. We have force F equal spring constant K multiplied by dx, change in length. From here, K equal F over dx, and we can count in that case what is the relative uncertainty for measurement of K is this one for Steve. For Tiffany, we have another formula. We have force 5 times greater. It means that enlargement will be 5 times greater for this spring, but absolute uncertainty is the same. It means that from here we can find that delta K for Tiffany equal to 0.2 delta K for Steve. And this is the answer C, and that was solution for problem number 23. Problem number 24. A mass M is connected to one end of a zero length spring with a spring constant K. The other end of the spring is connected to a frictionless bearing mounted around a horizontal pole so that the mass can swing in a vertical cycle of radius r around the pole. The setup is shown in the figure below. What is the vertical distance h between the center of the circular orbit and the axis of the pole? Assume that both the diameter of the pole and the rest length of the spring are negligible compared to r. Solution for problem number 24. This problem could be solved using a vector form. Let's write equation for total force acting on our mass. So total force equal negative K multiplied by vector L minus mg multiplied by unit vector j in the vertical direction. Here vector L, that's a vector from pole to our mass. We can represent vector L as a vector h, which is from pole to the center of rotation, plus vector r from center of rotation to our mass. And now we have this equation, and for point below the pole h to be center of rotation, we have to equalize second and third member to each other. kh equal mg and h equal mg over k, which is answer D, and that was solution for problem number 24. Problem number 25. A ball of a neglectable radius and mass m is connected to two ideal springs. Each spring has a rest length L0. The springs are connected to the ball inside a box of height 2L0, and the ball is allowed to come to equilibrium, as shown. Under what condition is this equilibrium point stable with respect to small horizontal displacements? Solution for problem number 25. First, let's find the position for equilibrium, which is below initial position in the middle of the box. We have minus k1z minus k2z equal mg, where z is a vertical displacement for equilibrium. From here we can find z. That will be negative mg over k1 plus k2. Now let's find what is the force created by upper string and lower string. Upper string will create pulling force and lower string will create pushing force. For upper string we have F1 equal K1Z, which is K1 mg over K1 plus K2, and for lower string we have F2 equal K2Z, which is K2 mg over K1 plus K2. Now let's do small horizontal displacement x. In this case, because change of length of this strings has a second order of smallest compared to x, we can count only part of horizontal change in force. For upper string we have x over L0 minus z multiplied by force F1, and for x2 we have x over L0 plus z multiplied by F2. Condition for stable equilibrium will be F1x plus F2x less than 0. It means that after putting all this expression to this inequality, we have this inequality. And now let's do counting. After some multiplications and manipulations, we have this inequality, and finally we have K1 minus K2 greater than mg over L0, which is answer C, and that was a solution for problem number 25.